Forget everything you know about tunneling. Forget drills, forget dynamite, forget the slow, grinding pain of boring through solid rock. During the height of the Cold War, the US government faced a simple, terrifying problem. How do you build secure, undetectable underground command and transport systems faster and deeper than anyone else on Earth? Their answer was a $5 billion vision of geological domination. They called it Project Subterrene. This wasn't a drill. It was a demonic nuclear-powered Earth Eater designed to move through solid granite not by pulverizing it, but by melting it. The melted walls. The machine used immense controlled heat, upwards of 1,000 degrees Celsius, to liquefy the rock at its nose. As the machine moved forward, the molten rock was forced outward and cooled instantly, leaving behind a tunnel lined with perfectly smooth, durable obsidian-like glass. No more structural supports needed. The tunnel was self-sealing, self-supporting, and permanent. The nuclear heart. To generate the heat required to melt stone, the subterrane needed a power source of impossible density and endurance. Its core was a compact nuclear reactor, a silent, mobile atomic furnace built to run for months, generating tunnels that could span continents, creating a truly undetectable, underground hyperloop for military assets, the fatal burial. The machine was a triumph of radical engineering, but it was doomed by its own genius. Once the subterrane started tunneling, it was too hot, too massive, and too radioactive to ever bring back to the surface. It was designed to run until it broke down, leaving a massive, lethal, nuclear hotspot permanently buried deep beneath the Earth. Stay with us as we dive into the terrifying physics and the fatal flaw of the nuclear mole. Because the US built the perfect stealth tunnel machine, only to realize the only safe place for the $5 billion monster was to leave it entombed forever. The science behind Project Subterrane was born at the Los Alamos National Laboratory, LANL, in the 1970s. The challenge was to overcome the inherent limitations of conventional tunnel boring machines, TBMs, which are slow, require massive logistical support, and leave behind tons of excavated waste rock that must be hauled to the surface. The subterrane concept replaced brute force with pure thermodynamics. The machine's blunt nose cone, or penetrator, contained high-temperature electric heaters, originally intended to be powered by a long-life, compact nuclear reactor. This penetrator would be heated to temperatures exceeding 1,000 degrees Celsius, 1832 degrees Fahrenheit, well above the melting point of most common rock formations like granite and basalt. As the hot penetrator pushed forward, the rock would liquefy into a viscous magma. The ingenious part of the design was the extrusion mechanism. The pressure of the advancing machine would force the molten rock outward and against the tunnel walls. Because the molten rock was constantly pressed against the cooler, ambient rock of the surrounding Earth, it would rapidly cool and solidify. The result was a tunnel with walls lined in a smooth, structurally perfect layer of volcanic glass or rock glaze. This glassy lining was impermeable to water, stable against seismic stress, and required absolutely no concrete or steel support. The tunnel was self-made, self-sealing, and utterly stable. This capability promised to reduce construction time by a factor of 10 and eliminate the massive logistical nightmare of waste disposal. The physicists had successfully turned a drill into a continuous subterranean glass factory, solving the logistical problem of debris, but creating an even greater, unanswerable problem of immense, perpetual heat. The military mission profile for Project Subterrane was deeply rooted in the strategic paranoia of the Cold War. The US needed secure, undetectable, and stable underground facilities that could withstand a nuclear exchange. But the ultimate ambition was far more aggressive. The subterrane was conceived as a weapon of subterranean stealth and infiltration. Its speed and structural efficiency made it ideal for several terrifying, classified scenarios. 1. Undetectable Hyperloop. Building massive, high-speed transport tunnels beneath the U.S. for moving strategic assets, ICBMs, command centers, and personnel, creating a nuclear-proof, hidden defense network. 2. Covert infiltration. tunneling rapidly and silently beneath enemy territory, potentially for surveillance, sabotage, or establishing forward operating bases close to Soviet command centers. The glassy, smooth walls and the lack of traditional boring noise made the subterrane virtually acoustically invisible to conventional seismic detection. 3. Resource access, providing stable, high-pressure tunnels for deep-sea mining or geothermal energy tapping, without the risks associated with conventional drilling. The concept was terrifyingly simple. The machine would start on the surface, descend to its operating depth, potentially miles deep, and then begin its journey, driven by its self-contained nuclear power. Because it left no waste rock, the only evidence of its passage was the perfectly sealed glass tunnel. The machine was a master of stealth, but this very capability, operating deep underground for months on end, introduced the fatal dilemma of maintenance and retrieval that would ultimately bury the project. The engineers at Los Alamos had solved the propulsion problem, but they fatally neglected the retrieval paradox. The Subterrene was designed for endurance, fueled by a compact nuclear reactor or by radioisotope thermal generators, RTGs, in smaller versions. This continuous power source was the heart of the machine's efficiency, but also the source of its inescapable danger. The penetrator nose had to remain intensely hot, over 1,000 degrees Celsius, not just while melting, but during its operation to prevent the molten rock from solidifying and permanently trapping the machine. Even when the power was theoretically turned down, the residual heat and radioactivity of the core meant that the Subterrene could not be safely approached or dismantled for months or even years. Imagine the scenario. The machine completes its 100-mile mission, or, more likely, it encounters a geological fault or mechanical failure deep underground. The tunnel lining is hot glass, and the machine itself is a massive radioactive furnace. It cannot be towed. It cannot be repaired. It cannot be abandoned immediately. Any attempt to recover the reactor would require months of specialized, highly dangerous work, effectively contaminating the entire retrieval team and the tunnel entrance. The simple, unanswerable question that Congress and the Department of Defense faced was, how do we service or retrieve a $5 billion, multi-ton nuclear hotspot buried 2 miles beneath a sensitive military installation? The only practical answer was permanent burial. The cost of building the tunnel was astronomical, but the potential cost of retrieving a single broken-down machine, the radioactive fallout, the personnel exposure, the required infrastructure, was deemed infinite. The brilliant engineering guaranteed the machine's ability to tunnel forever, but the same physics guaranteed it would be entombed forever, alive or dead. The greatest flaw of Project Subterrene was not technical failure, but unacceptable nuclear liability. The Subterrene was effectively a mobile, unshielded nuclear facility designed for one-way missions. Unlike the floating nuclear power plant, Sturgis, which could be towed and decommissioned in a dry dock, the Subterrane's radioactive core will be permanently lodged deep within the Earth's crust, far from any controlled containment facility. The risk of groundwater contamination was enormous. If the sealed glass walls cracked due to seismic activity or long-term geological stress, the unshielded radioactive material from the core could leak into the deep aquifer, leading to long-term contamination across vast territories. The entire concept violated the principle of containment. They were intentionally placing high-level radioactive waste, powered by an active core, into an unrecoverable, geologically complex environment. The political and environmental risk was non-negotiable. Furthermore, the strategic utility was rapidly overtaken by safer alternatives. By the mid-1970s, conventional TBMs had dramatically improved in speed and size. And while they still generated waste, they did not create a permanently buried nuclear time bomb on a national scale. The cost of building a traditional, steel-reinforced tunnel was a quantifiable expense. The cost of mitigating the environmental disaster of subterranean core failure was simply too high. The Subterrene was an engineering masterpiece, but it represented a strategic dead end that was too hot, too dangerous, and too permanent to survive the political shift towards nuclear caution. The fate of the project was sealed, but its technology found a short, bizarre, and highly classified afterlife in a final, smaller test to fuel the submarine's immense heat. The Los Alamos scientists explored two terrifying power options, both involving atomic energy, but with drastically different risks and capabilities. The size of the machine dictated a need for power density far beyond anything conventional. The primary goal was endurance and heat. The most ambitious version of the Subterrene required a compact, high-temperature nuclear fission reactor at its core. This reactor would run continuously, generating the necessary megawatts of power to melt granite. This was the ultimate design, promising months of nonstop tunneling, potentially beneath continents. But this was also the most dangerous option. A reactor failure deep underground meant a highly active core, unshielded by miles of concrete, permanently contaminating the local geology and water table. The second, smaller concept, used in the initial proof-of-concept tests, utilized radioisotope thermoelectric generators, RTGs, the same technology used to power deep space probes like Voyager and Curiosity. RTGs generate heat and electricity through the natural decay of highly radioactive isotopes like plutonium-238. This power source was smaller, more stable, and did not require complex cooling systems, but its heat output was limited. It could only melt softer rocks and was not capable of the high-speed, military-grade tunneling required by the Pentagon. The military quickly fixated on the fission reactor design. They wanted the speed and range of the high-power reactor, even while fully understanding the colossal, unmanageable risk. The very concept of putting a hot, active fission reactor into a remote, unrecoverable geological location was an unprecedented leap of faith or folly. The engineers had to design the reactor core itself to be incredibly robust, capable of withstanding the immense vibrations and pressures of drilling, ensuring the core didn't physically fragment and lose containment deep in the earth. They built a nuclear engine that was perfect for space, but lethally inappropriate for the Earth, setting the stage for the inevitable conflict between ambition and basic safety protocols. The Subterrane's unique method of tunneling created a series of unprecedented geological challenges that ultimately crippled the project's viability. The melting of rock does not result in neat, predictable tunnels. It creates a dynamic, high-temperature environment. The sheer volume of magma created by the melting rock posed an immediate problem. While the majority of the molten rock was forced against the walls to form the glassy liner, the machine had to manage the excess. In some designs, the excess magma was forced backward and allowed to solidify behind the machine. This required the machine to move at a very precise speed, too fast, and the pressure of the unsolidified lava could stall the motor. Too slow, and the excess lava could completely solidify around the penetrator, trapping the entire machine instantly. Furthermore, the geological composition was an active enemy. Hitting pockets of groundwater or underground ice at 1,000 degrees Celsius would lead to massive, immediate explosions of steam, threatening to destroy the machine and potentially collapse the tunnel. Hitting pockets of natural gas or oil could turn the tunneling process into a massive, uncontrolled inferno. The Subterrene required real-time, high-precision geological sensing to predict these obstacles, a capability that was unreliable in the 1970s. The constant flow of heat into the surrounding rock also created immense, localized thermal stress. The rock around the glass liner would expand and contract violently, leading to geological fractures and instability far beyond the tunnel itself. The perfect glassy lining, built to be stable, could easily be compromised by the massive heat stress it induced in the surrounding rock. The Subterrene was not just boring a hole. It was actively fighting and changing the geology around it, creating unpredictable instability that no engineer could safely guarantee. One of the primary military justifications for the Subterrene was acoustic stealth. Conventional TBMs generate massive noise and vibration detectable by seismic sensors miles away. The Subterrene, operating by melting, was relatively silent, a significant tactical advantage for covert operations. However, the machine's operation introduced a new, non-acoustic signature that was equally alarming. Thermal and seismic shock. The immense, constant heat radiating from a machine's penetrator created a predictable thermal signature that could be detected by sensitive underground thermal mapping equipment. While hard to detect from the surface, this signature could be mapped by forward reconnaissance systems. More crucially, the massive thermal stress and the controlled explosions of steam and gas as the machine encountered volatile pockets created unpredictable microseismic events. While quieter than a traditional drill, these events were often sharp, distinct, and highly localized. For intelligence agencies dedicated to monitoring underground activity, these signatures would be distinct indicators of clandestine tunneling. The military realized that the machine's silence was a strategic lie. It traded loud, predictable mechanical noise for subtle, but equally detectable geological noise. This realization complicated the covert mission profile immensely. The Subterrene was designed to be undetectable, yet the laws of physics dictated that a 1,000 degrees Celsius nuclear-powered machine could not simply disappear into the Earth without leaving a detectable signature. The machine's own ambition had betrayed its stealth, forcing the U.S. government to confront the moral cost of burying such a high-value, lethal asset. The true political and ethical breaking point for Project Subterrene was the explicit design requirement to abandon the nuclear core deep underground. This was not an accident. It was the plan. The concept was that the tunnel itself was the priority, and the machine, too hot and too contaminated to be retrieved, would be intentionally entombed. Upon mission completion or mechanical failure, the penetrator would be electrically sealed, and the back section of the tunnel would be sealed with rapidly setting concrete or a self-sealing chemical mixture. The machine would then become a permanent, unrecoverable, radioactive hotspot. The ethical ramifications were immense. The U.S. would be deliberately placing high-level nuclear waste, an active, fissionable core, into an uncontrolled geological environment, risking future contamination of aquifers and leaving a permanent hazard for future generations. This was a direct, dangerous violation of the principles of nuclear waste containment, which mandate retrievability and long-term surface monitoring. The political backlash from the scientific community and internal government watchdogs was growing. They argued that the short-term strategic gain of a glassy tunnel did not justify the infinite environmental liability. The Subterrene was not just expensive, it was morally bankrupt. No amount of military necessity could justify creating hundreds of permanent, buried nuclear time bombs across the continental U.S. or international territory. The decision to cancel the project was not an engineering verdict. It was an ethical one, forcing the military to find safer, if slower, ways to achieve subterranean dominance. This left the engineers with a final, smaller, and less risky test to prove the melting physics worked. A test that resulted in a fascinating, yet forgotten, piece of technology. Before the fission-powered Subterrene was fully funded and built, the Los Alamos team conducted successful, albeit smaller-scale, proof-of-concept tests. These tests did not use the full-scale, massive fission reactor, but rather smaller, safer electric resistance heaters or RTG simulators. The most crucial demonstration involved a small, electrically heated penetrator. This test successfully proved the core principle. Rock could indeed be melted and fused into a stable, glassy tunnel lining. The resulting tunnels were small, often just a few inches to a foot in diameter, but the obsidian-like walls were perfectly formed and highly resistant to collapse. This technological success was undeniable. The physics worked. The project was officially canceled by the Atomic Energy Commission, EC, in mid-1970s. Not due to the failure of the technology, but due to the unacceptable nuclear liability and cost of decommissioning and disposal. The failure was strategic and ethical, not scientific. However, the technology found a final, bizarre niche. The smaller, RTG-powered subterranean concepts were briefly studied for potential use in geological exploration and oil and gas drilling. An RTG-powered probe could silently melt through hard-to-reach rock formations, providing core samples without the vibration and noise of conventional drills. While this application never achieved wide commercial use, the research demonstrated that the Subterrane's technology was not inherently lethal. It was the military's demand for raw, unstoppable power and non-retrieval that doomed it. The $5 billion project left behind a legacy of perfect, silent, glassy tunnels, a permanent, physical reminder that the nuclear mole was too brilliant, too hot, and too costly to ever become a reality. The total cancellation of the Subterrene project was a strategic defeat, but the high-temperature physics developed at Los Alamos did not vanish. The core concept of using heat instead of steel found a crucial, albeit dramatically scaled-down and non-nuclear, niche, geothermal energy and extreme geological sampling. While the military subterrane was a massive, monstrous tunnel maker, the smaller, electrically powered penetrators proved invaluable for deep scientific research. The technology was quietly adapted into specialized probes known as rock-melting earth-penetrating probes, MEPs. These probes, often just inches in diameter, were used to sample highly resistant, deep geological strata. The physics solved a major logistical problem. The advantage was in endurance and thermal resilience. When a conventional drill bit wears out, you must pull up kilometers of drill string, replace the bit, and start over, a process costing millions and taking weeks. The MEP probe, when its material was stressed, could simply melt its way forward, sinking into zones of extreme temperature and pressure that conventional drills couldn't touch. One of the most profound applications was in hot, dry rock geothermal energy. To tap the Earth's immense internal heat, engineers must drill boreholes to extreme depths where rock temperatures are hundreds of degrees. Here, the melting technology showed its superior resistance to thermal shock. Subterrene, which failed as a weapon, quietly caused a revolution in how scientists study our planet's interior. Its legacy is not glass tunnels under Moscow, but small, silent probes that still explore the deepest, hottest, and most mysterious corners of the Earth, proving that the original Los Alamos idea was at least physically sound. The official narrative is clean. Project Subterrene was canceled due to environmental risk. But what happened to the actual prototypes and test tunnels created during its existence? This is where the deepest secrecy lies. Because the key test apparatus used radioisotope thermoelectric generators, RTGs, fueled by highly potent plutonium-238, or were powered by intense electricity, they left behind a highly toxic, radioactive signature. The remnants of these tests, conducted deep within the New Mexico desert and in top-secret underground laboratories, were highly classified and, most significantly, were permanently sealed. Imagine the scenario. A smaller prototype subterrane gets hopelessly stuck hundreds of feet down. It doesn't have an active reactor, but its hull is contaminated. You cannot retrieve it. According to the strict nuclear waste protocols, the safest and cheapest solution was to hermetically seal the tunnel section, leaving the machine and its dangerous components entombed inside a glassy coffin. Today, while the specific coordinates remain classified, geological maps of the Los Alamos region must bear marks for no-dig zones or high thermal stress areas, locations where the unique glassy tunnel lining and the buried, radioactive machine remain. These buried machines, sealed in their own perfect glass tombs, are the physical proof of the Cold War's greatest fear, creating a technology so destructive and so volatile that the only way to control it is to bury it forever. The $5 billion was spent to create permanent, irreversible nuclear ruins. 60 years later, the dream of fast, cheap underground transport networks has returned. But now, it is led not by generals, but by entrepreneurs. We're talking about the Boring Company and the drive to create the Hyperloop, a massive underground transportation system. These modern builders face the exact same fundamental problem that Los Alamos faced in the 70s, the crippling cost and speed of drilling. Everyone building tunnels today knows that traditional tunnel boring machines, TBMs, are slow, expensive, and generate excess waste. Elon Musk and others have publicly championed the need for a revolution in tunneling technology. While they are clearly not using a nuclear reactor, Their engineers are actively pursuing the scientific legacy of Subterrene. They are exploring ways to enhance efficiency through extreme heat or advanced rock fracturing, seeking the same self-sealing, stable, glass-lined tunnel that the Subterrene promised, but without the toxic fee. The problem of the Subterrene was power. Modern technologies, such as plasma drilling or thermal spallation, rock chipping, seek to achieve the melting or fracturing effect using immense electrical power from conventional sources, rather than plutonium. They aim for those perfect, self-sealing glassy walls, but without the contamination. Thus, the $5 billion spent on Subterrene was not merely a cancellation. It was the world's most expensive scientific experiment on the limits of feasibility. The project proved that melting rock is possible, but it clearly established the ethical red line. Never combine that capability with non-retrievable nuclear fuel in an uncontrollable environment. Let's condense the absolute, unassailable reasons why the nuclear mole was the ultimate never-built military project. It was a perfect storm of three catastrophic miscalculations. Fatal flaw number one: the exponential cost, the $5 billion lie. The true financial price of a submarine tunnel was not just the cost of the steel and the fuel. It was the cost of total non-retrievability. Every single machine that got stuck, broke down, or completed its mission became an unmovable, radioactive, $5 billion asset that had to be permanently buried. The inability to repair or reuse the apparatus transformed it from a strategic tool into a perpetual, unmanageable liability. Fatal flaw number two: the infinite nuclear liability. Subterrene was a deliberate decision to place a highly active nuclear core outside of any regulatory containment system, deep within a geologically complex and unpredictable environment. This created a never-ending environmental risk of aquifer contamination, establishing a moral and political taboo that even the Cold War Pentagon could not override. Fatal flaw number three: strategic redundancy. The problem was solved better. In the end, the Subterrene was an attempt to solve a problem that was already being solved more safely. While Los Alamos melted rock, other engineers rapidly advanced conventional TBMs and developed new, faster methods of concrete shoring. These methods were slower, but they were clean, controllable, and predictable. In military logistics, where risk mitigation is paramount, predictability always outweighs uncontrollable genius. The nuclear mole was a brilliant engineering monstrosity that proved, sometimes, the fastest and most efficient path is also the most dangerous, and must therefore be left forever buried. The Subterrene project left us with a powerful, haunting question. Our world needs subterranean infrastructure more than ever before. We are building subways, hyperloops, and deep storage facilities. 60 years later, the world's greatest engineering minds are looking again at the idea of melting stone, chasing the same perfect, self-sealing glass wall that the Subterrene created. But will humanity ever be ready for this technology? Los Alamos proved we can melt the earth. But we also proved that we cannot control the consequences of burying the power source needed to do it. What is scarier, slowly building a tunnel, or instantly creating an irreversible, eternal nuclear graveyard? We want to know your opinion. Considering the massive advancements in robotics, remote control, and clean energy, can modern engineers create a safe, non-nuclear version of the Subterrene that can melt rock without the risk of burying itself and poisoning the water? Or have the laws of economics and nuclear liability permanently interred the nuclear mole? Join the discussion and let us know your predictions for the future of subterranean travel in the comments below.